Hi, my name is Wyatt Newman. Today we're out in the wilderness for Mrs. Stewart's final project, and we're learning about cyanobacteria. Cyanobacteria is also called blue-green algae. They are microorganisms that structurally resemble bacteria. They lack a nucleus and organelles. This name is convenient for talking about organisms in the water that make their own food, but does not reflect any relationship between the cyanobacteria and other organisms called algae. Cyanobacteria are relatives of the bacteria, not eukaryotes, and is only the chloroplast in eukaryotic algae to which the cyanobacteria are related. Cyanobacteria contain chlorophyll and conduct oxygenic photosynthesis. Cyanobacteria are approximately 2.5 billion years old and thus are the oldest oxygenic phototrophs on Earth. Cyanobacteria exhibit remarkable adaptations to global change. They tolerate desiccation and high ultraviolet light conditions often for many years. Over their long evolutionary history, they have formed numerous endosymbiotic and mutualistic associations with microorganisms, higher plants, and animals. This includes seagrass, sponges, and even polar bears. Cyanobacteria have also exploited man-made pollution of aquatic environments. Cyanobacterial blooms are highly visible, widespread indicators of eutrophication. Because of the toxicity of some bloom taxa, blooms can pose serious water quality and animal and human health problems. Foul odor and tastes, oxygen depletion, fish kills, and drinking recreational impairment of symptoms of bloom-infested waters. Finally, the large contribution of cyanobacterial blooms to phytoplankton biomass and ecosystem nutrient fluxes can alter biogeochemical cycling and food web dynamics. Cyanobacteria are important providers of nitrogen fertilizer in the cultivation of rice and beans. The cyanobacteria have also been tremendously important in shaping the course of evolution and ecological change throughout Earth's history. The oxygen atmosphere that we depend on was generated by numerous cyanobacteria. Sometimes cyanobacteria begin to take residence with certain eukaryotic cells, making food for the eukaryotic host in return for a home. This event is known as endosymbiosis and is also the origin of the eukaryotic mitochondria. Cyanobacteria are aquatic and photosynthetic, that is, they live in water and can manufacture their own food. Because they are bacteria, they are quite small and usually unicellular, though they often grow in colonies large enough to see. They have the distinction of being the oldest known fossils, more than 3.5 billion years old. In fact, it may surprise you to know that the cyanobacteria are still around. They are one of the largest and most important groups of bacteria on Earth. Well, how fast exactly do they grow? Let's go back to the camp and find out. Alright, now that we're finally back at camp, now we can get started on the problem. So, the problem that we're going to be solving is if a culture of 500 cyanobacteria is permitted to grow under natural conditions in a petri dish, after how much time will the amount of bacteria triple in the dish, given that cyanobacteria has a growth rate of 1.7 per day. I found that information of the growth rate from a PDF file, which I will show you my sources, and it says that it's 3.1 to 1.4 doublings per day, which means that if it's 0.3 and 0.4, we're going to times both of those by 2, and that's going to get us 0.6 and 2.8. Now we're going to find I just found the average between them, so I added them up, and then I divided by 2. It equals 1.7. So that's how I got the 1.7 per day. And we're going to use that in our equation. Now the next thing we're going to know is, or need to find is, the thing that we're going to need to use is the exponential growth equation, which I'm going to write in red so everybody can see it a little bit easier. It's y equals a b to the x. Okay, so now we're going to try to find b. So we can find that, and there's different ways to write it. So I'm just going to write stuff down. Okay, but what I used is that 1.7 equaled b because x is going to equal 1 day. So that's just going to turn this into a big 1, and that's going to, and b to the first of anything is always 1, or that number. So it's going to be 1.7. So plugging that in, it's going to be y equals a 1.7 t. Okay, so t is for time, which is easier for me to remember because x and all that stuff gets pretty confusing, since everything is always with x and y. So we know that a, because it says that a culture of 500 cyanobacteria, so we know that the starting value is 500. So we're going to plug that in for a. So it's going to be y equals 500, 1.7 to the t. And then from here, we're going to go back up to the equation because we always want to pull things from the problem, because in the problem they'll tell us what needs to happen with everything else. So the next thing we're going to look at is triple. So we're going to have to triple the starting amount so we can find how many days it takes to triple it. So it's 500 times 3, which equals 1500. Okay. So now we have the full equation. So it's 1500 cyanobacteria, 500, 1.7 to the t. Okay, so now we have to find t, which is what we set out to do, is how long it takes in days. So we're going to divide both sides by 500. And that's going to equal 3 equals 1.7 to the t. Okay, now to solve the rest of this, we're going to use natural logs. We're going to find the natural log of 3 equals the natural log of 1.7 t. Okay, so what I did is I just divided both of these by the natural log of 1.7. So that's going to look like this. And if you plug it into your calculator, which I have right here, but I don't know if you'll be able to see it because it's pretty blurry. So it's the natural log of 3, which you gotta make sure you end the quotations, divided by the natural log of 1.7. Alright, now this equals, and you can see a little bit, it's 2.070399166. Okay, so now that we know that's that, we found it, but up here, I remember at the top, it says round to the nearest thousandths. So we're going to take this, we're going to find tens, hundredths, thousandths. You do not round, so this kind of goes away. So t equals 2.070 days. Alright, so this is what we were looking for, and we found it, so I guess we're all doing good so far. So that's how we solve it with the equation, and we have all the problems set out. Alright, so the next thing that we're going to do is we're going to solve this using graphing. Graphing's a little different. I was considering graphing it myself, and then I realized that since everybody either should learn how or already knows how, we can use the calculator. So we have the equation right here, and that's 500 times 1.7 to the t, which is time, and what we wanted to find, which we found in the equation. So we're going to go to our scatter plot y right here to the top, and I already have it plugged in, so that's let's go down a little bit. So it's 500 times 1.7, and I have the x up here because I wasn't sure how to put t, and since it's x anyway. So then we're going to hit graph, which is this button up here to the right top corner. We're going to hit graph, and we're going to get this really big, massive graph with a window that is just all-time crazy, like 14 something. So we're going to go back to the graph, and then I use trace. And what we're looking for is we're looking for this to equal, oh, that's really hard to see. So that's going to equal 2.070, as close as we possibly can get. And this we want to get to 500 as close as we possibly can get. So since you're clearly a little hard to see, I'll try to find it for you. So it's, and you can do this on any calculator except that's not graphing, clearly you can't use those, but you can use these. So right here on this value, I found 2.0700166, and on the y I found 1499.6955, And that is as close as you can get. Now you can zoom, and you can always zoom in, and you can get closer and closer to the value. And it just got a little bit closer. And you can keep going and keep going. My calculator will not go any farther, but some will. So other than that, you can just keep going and that'll be fine. Alright, so next we're going to solve it with our data table. Our data table is right here. So we know that the equation equals 500 times 1.7 to the t, which I've said a million times, which is very important to use in both graphing and the data table. So since we know that it's starting, so t is starting out, so these values right here, all the ones on the left side are the times, are the days. So since we go back up to the top, since 0, we start out with 500. So we know that in 0 days, which is what we started out with, it's 500. And as we say, it's 0.1 of the day, it goes up, and it goes up, and each little bit of the day, it keeps increasing. So through this, we're going to go all the way down till we can find the closest thing to 5,000 on the right side, which is the value of cyanobacteria. So we go all the way down, and we're going to go to 2 and 2.1, because 2, as you can see right there, is 1,445, and 2.1 is 1,523.7. Hope that we covered that up. So, since we know that's going to be in between these two. So, now, since I was already knew that, I printed up a whole nother sheet to go on top of this. So, on this part, I made it a smaller window. So it goes just from 2 to 2.1, and it goes by hundredths, which is easier to find how close it can get. So we know that 2, of course, was 1,445. So we're going to go do the same thing. We're going to go down all the way till we can find what's closest to 15,000. So we know that 2.7 and 2.07 and 2.08 are going to be the closest, because that's, if you round that number, it's going to get to 5,000, and this number is extremely close. Not 5,000, excuse me, 15,000. Okay, so now we're going to go back to a smaller window, which is between 2.7 and 2.07 and 2.08. So you can keep going and keep going and keep going into the thousands and all the decimals and all that stuff. I'm going to stop here because it can just keep going on and forever until we actually find the exact amount, and it's going to be exactly 5,000 or 15,000. I don't know why I keep saying 5,000. Okay, so what we're doing here is we're going to go look for the exact same thing that we were doing. We're going to find on the right side the things closest to 15,000, and as we can see, that's going to be the top two numbers. But this number, if you round it, it's going to make this 15,001. This, if you round, it's going to be 15,000. So this number is going to be the closest, rounded to the thousandths place, like we said at the beginning of the problem. So this is going to be correct. Alright, so now, since we just solved it in all three different ways, we're going to go, and I'm going to show you real quickly my introduction that I said at the beginning. It's all this information. If you would like to pause the video to look at it, it's perfectly okay, and you can read it, and I'll be emailing anyway, so here's the last part of it. Okay, and now these are my sources. This is the PDF file that I used, that I showed you at the beginning of the video, that told me the growth rate of it. This is just all the information I got about cyanobacteria, which is actually very interesting to learn about. And I believe that is it. So thank you very much, and that's it.